Lesson 6.6, linear functions from two data points. Our objective for this lesson is to be able to create an equation for a linear function based on two given data points. We're going to use 3 steps to create a linear function from two data points. Step 1 is to find the rate of change, also known as the slope of the function, using the rate of change formula that we learned in lesson 6.5. Rate of change is equal to the change in the dependent variable, or the change in y, divided by the change in the independent variable, or the change in x. Once we've found that rate of change, then step 2 is to choose one data point, it doesn't matter which one, and plug in the independent variable for x, the dependent variable for y, and the rate of change that we found in step 1 for m in the equation y equals mx plus b. You can then solve for the initial value b because it will be the only unknown left in the equation. So in step 1 we found the rate of change, that's our m, and then for y and x we're going to choose one of our data points, and we're going to plug in the x value for x and the y value for y. And now the only unknown left is b, and so we can solve for b and find the initial value. Step 3 then is to use the rate of change and initial value to write the equation of the linear function in the form y equals mx plus b. So step 1 was to find the rate of change, that was our m. Step 2 was to find our initial value, that's our b, and now we just plug those two values into this equation, y equals mx plus b. Plug in the rate of change for m and the initial value for b. Our example says that in 1912, the world record in the men's 100-meter run was 10.6 seconds. The world record dropped to more than a full second below that in 2009 when Usain Bolt ran 100 meters in 9.58 seconds. Use these two data points to create a linear model that describes the change in the men's 100-meter world record with time. Interpret the model and discuss its validity. So the first thing that I want to do is define my dependent and independent variables. So the two quantities that we're working with here are the men's 100-meter world record time and the year. And it seems that the world record time it depends on the year, because the more years that pass, the lower the world record time is becoming. So our dependent variable is going to be the 100-meter world record time. And the independent variable will be the year. Now, if we just put in the year, 1912 and 2009, that will mean that our initial value, the initial year that we're looking at, is the year 0, 2,000 years ago. And so when we're working with years, we usually try to find some closer year that's going to be more relevant. Like 1912, we could do years since 1912. That would mean that our initial year was 1912, and so our initial world record time, our initial value, would be 10.6. But in order to demonstrate the 3 steps that I talked about earlier, I'm going to make this 1900. It's a nice round year, and that way, if we say x equals 60, for example, we know that that means 1960. All right, so let's find the two data points. Now that we've defined our dependent and independent variables, let's write out what the data points that we're working with are. So in 1912, which is an x value of 12, the 100-meter world record was 10.6. And in 2009, which would be an x value of 109, the 100-meter world record time was 9.58. All right, so now we have two data points. And the first step is to find the rate of change. So the rate of change is going to be the change in the dependent variable, so the change in the 100-meter world record time. That is going to be 9.58 minus 10.6. We, because it went from 10.6 to 9.58, so the change is going to be 9.58 minus 10.6. And we're going to divide that by the change in our independent variable years since 1900. So that's going to be 109 minus 12. And make sure that these values straight above one another correspond to one another. So 9.58, that happened in the year 2009, and 10.6, that happened in the year 2012, just to make sure that you're subtracting in the right order. All right, so this is going to be negative 1.02 divided by 97. That means that the world record time came down by 1.02 seconds over 97 years. And if we divide that out, we get negative 0.01052. Now, it may seem natural to round this to negative 0.01, but I'm going to go ahead and keep all of those digits there, and I'll show you why in just a minute. All right, so that's our first step. Our second step is to find our initial value, and we're going to do that by using the formula y equals mx plus b, and we know m is negative 0.01052, and we've got two data sets that we can choose from where we have an x value and a y value. So let's just choose this first data set. It doesn't matter which one we use, so we'll choose the easiest one to work with, and we'll plug in our y value, which is 10.6, is equal to our slope, which was negative 0.01052. That's our rate of change, or our slope, and then the x value was 12 plus b. And if we do our algebra here, multiply this across and then add that to both sides, we get that b is equal to 10.72624. And again, I'm carrying this out to 5 decimal places. And then now that we've got our b and we've got our m, we're ready to just plug these in to y equals mx plus b, and that'll be our model. So we get y equals our rate of change, so negative 0.01052 x plus our initial value of 10.72624. That's going to be our model. Now we want to check this to make sure that that both of these data points are going to make this equation true. And we know that this one will, because that's how we came up with our b. But let's plug in this. If we plug in 109 for x, then we get a y of 9.579 something. So we're really close to being right on 9.58. The reason that I carried this out to 5 decimal places, by the way, is so that this model will work to predict the world record time in 2009. You want to be careful about rounding off too much. You want to keep as many decimal places as are necessary to at least be able to predict both of the data points with your model. All right, the last thing to talk about is the validity of this model. Well, over this time period, it actually works pretty well. If you were to plug in, say, x equals 60 and carry this out, your y value is going to be pretty close to the world record in 1960. It actually works pretty well between the years 1912 and 2009. Of course, it can't work forever. What this rate of change means is that we're lowering the world record by about 100th of a second every year. And if we were to continue to do that, in about 500 years, people would be running faster than Formula One race cars. And in 1,000 years, we'd actually get to a time that's less than zero.